In Chapter 15, we talk about thermodynamic processes in which we change the energy of a system by adding heat or removing heat or doing work. So for these problems, we're going to use the first law of thermodynamics, which states that the change in internal energy, which is 3/2 times the number of particles times K times the change in temperature from Chapter 13, is equal to heat Q minus W. It's important when we do this to get our signs right. Q is positive if heat is added, and negative if heat is removed. And for work, the work is positive if it's done by the system, and negative if it's done on the system. And this definition may be different, it might be opposite for some of these to what you have in chemistry. So make sure when you're doing the problems in this chapter that you remember the way that we define these. Okay, so this problem says that a system takes in 500 joules of heat. So Q is going to be plus 550 because that's added to the system. And it does 840 joules of work. So W is also done by the system. So 840 joules plus. So the change in internal energy is Q minus W, 550 minus 840, which is negative 290 joules. So it's a negative change in internal energy. So that means that the temperature of the system would drop. Part B, the internal energy of the system increases by 400 joules. So delta U is equal to plus 400. 500 joules of work are performed on it. So that's work done on the system. So that's going to be negative 500 joules. And what we want to know is what was the heat flow into or out of the system. All right, so if I rearrange my equation, remember U is equal to Q minus W. So that means Q is equal to delta U plus W. So now I know delta U and W, so let's plug it in. It's 400 plus negative 500 for the work. So I get negative 100 joules. Okay, so the amount of heat is 100 joules, and it flows out of the system. Now let's look a little bit more specifically at examples of what's going on. So I've got a monatomic ideal gas at 27 degrees C, undergoes a constant pressure process from A to B in figure A. So I'm going at 2 atmosphere, I'm going from a volume of 1 liter to 2 liters. And then from B to C, I'm going to stay at a constant volume of 2 liters. I'm going to come down in pressure from 2 atmospheres to 1 atmosphere. I want to find the total work done during these two processes. Okay, so we want to know what are the works during the different processes. So constant pressure, our work is equal to the pressure times the change in volume. And a constant volume process, the work is 0 because there's no change in volume. Okay, so if I go from A to B, work from A to B is equal to the pressure, and now I need to put my pressure into standard units to get my work in joules. So it's going to be 2 atmospheres times 1.01 times 10 to the 3 pascals per atmosphere times the change in volume. And now my change in volume, I go from 2 liters to 1 liter. Okay, so delta V is equal to 2 liters minus 1 liter, which is 1 liter. And I need to put that into cubic meters. Now there's 1,000 liters per cubic meter. So this is 10 to the minus 3 cubic meters. So 1 times 10 to the minus 3 meters cubed is my delta V. And so I get 2.02 joules of work that's done by the system and going from A to B. How about when I go from B to C? Well, since that's an isovolumetric, constant volume process, the work is 0, so the total work is just 2.02 joules. Okay, does it matter what the temperature was? No, it doesn't come into it. Does it matter that it's monatomic? No, that also doesn't come into it. Okay, let's do the same problem, but now we're going to look at figure B. So now we're going to go first, we're going to decrease the pressure. We'll stay in a constant volume. And then we're going to increase the volume. We'll stay in a constant pressure. And we want to find the work done. Do you think the work will be the same as it was for the previous one? Okay, well, let's look at what our problem is. So we've got now work from A to B is going to be constant volume, and that work is 0. Work from B to C is going to be P delta V. So now my pressure, and remember it's 1 atmosphere, I've got to put that into pascals. So 1.01 times 10 to the 3 pascals in 1 atmosphere. And then my change in volume, now again I'm going 1 liter, so that's 1 times 10 to the minus 3 cubic meters, and I get the work done is 1.01 joules. Okay, so my total work is equal to work AB plus work BC, which is 1.01 joules. Okay, so that amount of work is less, in fact it's half of what it was for problem 2. Okay, can we look at the picture and see that this should be true? Well, not quite, because we can't see it exactly to scale, because our axis actually should go down to here to be 0 atmosphere. Okay, so if I extend that to here, now remember the work done in a pressure volume curve is the area under the curve. So the work done for part 1, problem number 2, is this amount. The work done for problem number 3, if I extend this down to 0, is the area under the curve, which is that amount. And you can see that this is roughly half of that. So we've done isobaric, which is constant pressure. We've done isovolumetric or isochoric, which is constant volume. Now let's do an isothermal expansion. So isothermal means that we have a constant temperature. Okay, so we've got a monatomic ideal gas. It's initially got a pressure of 2 atmospheres. And let's straight away put that into pascals, 2.02 times 10 to the 3 pascals. And it has an initial volume of 8 liters, or 8 times 10 to the negative 3 cubic meters. It expands isothermally from 8 liters to 16 liters. So the final volume is 16 liters, or 16 times 10 to the minus 3 cubic meters. The final pressure, I don't know. And I know that the temperature is the same for both, because it's an isothermal process. So what's the final pressure of the gas? Well, remember, ideal gas law, PV equals nRT. Okay, so if we have an isothermal process, then everything on this side of the equation, the nRT, stays constant. So we have P times V is constant. So P initial, V initial equals P final, V final. So P final is equal to P initial, V initial over V final. So I've got 2.02 times 10 to the 3 pascals times 8 times 10 to the minus 3 cubic meters divided by final volume 16 times 10 to the minus 3 cubic meters. And so we can see our final pressure, we doubled the volume, and so we've halved the pressure. So we're going to have 1 atmosphere, 1.01 times 10 to the 3 pascals, or 1 atmosphere. Okay, so I've got final pressure, Now I want to know how much work is done in the expansion. So what's our equation for isothermal expansion? Work is equal to nRT times the log of V final over V initial. So what's nRT? Well, we can figure it out. It's just P times V, right? So let's find what nRT is. nRT, and we can use either initial or final. Let's use initial because we have it. So it's going to be 2.02 times 8. So I get 16.16. So the work is equal to 16.16 times the natural log of V final over V initial. Now I can leave this in liters if I want to, or put in cubic meters. Since I'm doing a quotient, the conversion would cancel out anyway. So I'm going to do natural log of 16 over 8, natural log of 2, times 16.16, and I get my work is 11.2 joules. If we'd been asked, we could also have found what the temperature was, as long as they'd given us how many moles of gas. Since they don't give us how many moles of gas, we can't find out what the temperature is. Now note here, I had to put my pressure and volume into the standard units in order to get my work into joules. The second part of the chapter talks about engines and refrigerators. The efficiency of an engine is equal to the work done by the engine divided by the heat that it absorbs, and that's also equal to 1 minus the heat given to the low temperature reservoir, or the heat released, divided by the heat given in. Okay, so we're told the efficiency is 0.21 or 21%, and they want to know for every 1,000 joules absorbed by the engine, so that's QH, we want to know how much work is done by it, what's W, and how much heat is released to it, so that's what's QL. Okay, so we know QH is equal to 1,000 joules, 1 kilojoules. We know the efficiency is 0.21. They want us to find part A, the work, and part B, QL. So for part A, E is equal to W over QH. So therefore, W is equal to E times QH. So it's the efficiency 0.21 times 1,000, which would give you 210 joules. And so there's 210 joules of work done by the system. For part B, now we're going to do a little bit more algebra because we need to find QL. So there's my equation. I want to rearrange it to solve for QL. So first of all, let me do QL over QH is equal to 1 minus E. How did I do that? First I added QL plus QH to both sides. Then I subtracted E. Okay, so now QL is equal to 1 minus E times QH. And I know everything there, so now I do 1 minus 0.21 times QH, which is 1,000. And I get 790 joules. Okay, so 790 joules of heat goes out, it's exhausted. We do 210 joules of work, and we use 1,000 joules of heat. Next question, for a specific kind of engine called a Carnot engine, we want to know what's the efficiency if it operates between reservoirs with temperatures of 20 degrees C for the low temperature and 200 for the high temperature. Well, for a Carnot engine, the efficiency is 1 minus TL over TH. Okay, we know TL is 20 degrees C. I need to put that into Kelvin, so that's 293.15 Kelvin. TH is 200 degrees C, so that's 473.15 Kelvin. So now I can just substitute those in. The efficiency is 1 minus 293.15 over 473.15. And you can see that if you had done this in degrees C instead of Kelvin, you'd have a very different answer. And we get 0.38. So my efficiency is 38%. Remember to go from a decimal to a percent multiplied by 100. Okay, last question. We're going to do a refrigerator rather than an engine. So the idea for a refrigerator is that the coefficient of performance is equal to the amount of heat that you pull out of the cold thing. Remember, you want to take heat out of your fridge and dump it into the room, and you have to do work in order to do that. That's also equal to the temperature of the low reservoir divided by the difference between the temperature of hot and cold. So I can get this because I know the temperatures. And say if I do 1,000 joules of work, how much heat do I remove from the fridge? So that's QL. So QL is equal to the heat removed. QH is equal to the heat exhausted. And we'll talk about that in a minute. And TL and TH are the temperatures of the low and high temperature reservoir in Kelvin. Okay, so low temperature reservoir is at 0 degrees C, so it's 273.15 Kelvin. Remember, it's got to be in Kelvin. TH is the temperature of the room. So that's 273.15 plus 40, or 313.15 Kelvin. So we can get the coefficient of performance is TL over TH minus TL. So it's 273.15 over 313.15 minus 273.15. So the coefficient of performance is 6.829. Let's keep a bunch of sig figs. Okay, so I've got the coefficient of performance, and I want to know QL, and I want to know QH. Okay, so first of all, I know my work is equal to 1,000 joules. Okay, so I can get from coefficient performance equals QL over W. I can get that QL is equal to the coefficient of performance times the work. So it's 6.829 times 1,000, or 6,829 joules. How much heat is exhausted? Well, QH, in order for energy to be conserved, is equal to QL plus W. So it's going to be 7,829 joules. So this is answer for part A and part B.